Yeah, so thank you so much, Morgan, for the invitation, and thank you all for coming. This is both the last day of the workshop and the first talk of the day, so I'm, really, really grateful that you could all make it. Yeah, so today I'll tell you about some recent work that we call probably approximately correct labels. This is joint work with Emmanuel Candes and Andrew Ilyas. Okay, so if we take a bird's eye view of data science, machine learning, we often see the following pipeline. We first collect a bunch of unlabeled data. Then we proceed to collect labels for all of those unlabeled data points. And then once we have a fully labeled data set, we can perform all kinds of downstream analyses. We can compute causal effects, train machine learning models, do all kinds of things. And the step in the pipeline that I want to focus on today, which I think we often take for granted, is the second step where we collect labels, because this is in reality often very, very slow and costly. So this often involves things like running very expensive biological experiments, or maybe collecting large amounts of human annotated data. So this is really a bottleneck in a lot of scientific applications. So the question that we want to ask today is, can we label data sets more cost efficiently without compromising data set quality? And so, of course, we can't not compromise data set quality at all. So we'll try not to compromise data set quality all that much while being more efficient at our labeling process. Okay, so I want to describe the formal setup that we'll be working with. So we will have capital N unlabeled data points that we'll denote by xi. And for each of these unlabeled data points, there is some label yi that we wish we had, but we don't. And so we're not going to make any distributional assumptions on these data points. We're just going to treat them as fixed. In addition to this data, we'll also have an AI model that we'll denote by f. And you can think of this AI model as something that we can, in principle, use to impute all of these labels that we don't have. So this AI model can be like ChatGPT. And our goal in the setup is to return a labeled version of this data set. So we want to return pairs xi, yi, tilde, where here I'm intentionally using tilde just to indicate that this might not be like a true label yi, but it's whatever we come up with. And the degree of freedom that we'll have is we'll be able to make this yi tilde either an expert label yi. So I'll say expert labels for labels that are like, you should think of them as ground truth labels. I try not to say ground truth because often there's no such thing as ground truth, but there's just like an expert source of supervision. Or alternatively, they can be AI predictions that we'll denote by yi hat. And you should think of these expert labels as being a lot more expensive than these cheap AI predictions. Okay, so what is the criterion that we want to meet? So we want to return this labeled data set while collecting as few of these expert labels as possible, such that for some loss function that we pick and denote by L, the average loss over this labeling is bounded by epsilon with probability 1 minus alpha. So just to make this a little bit more concrete, if we're in a classification setting, all these labels are discrete, we can pick the loss just to be the 0-1 loss, in which case this will be saying we want, let's say, 95% of the labels to be correct with probability 95%. Okay, so this is basically the problem setup, and we call this criterion here probably approximately correct labels or PAC labels because it has conceptual similarities with PAC learning. Okay, are there any questions about the problem setup? Because this is the basic definition we'll be working with. Yeah.
But we're finding like the errors here are even adversarial, right? We just want to bound them out, like the fraction.
So it depends on how you pick your loss. If you pick the 0-1 loss, that will be the case. We're going to show examples where the loss is not necessarily the 0-1 loss. So the loss can be like squared loss, or it could be sensitive to the magnitude.
Yeah, my point is more so like we don't have any distributional assumption on the mistakes.
Oh, no. Oh, yeah. So we're going to treat everything as fixed. Yeah.
We just understand the difference with in-sample regression is that we can choose which yi we observe.
Yes, we can choose which yi we observe. Yeah. At the beginning, everything is not observed, and then we're going to see, the whole point will be to pick where we observe the yi's. Yeah. Yes.
In order to do this, am I allowed to do some sample splitting to calibrate something?
That's essentially what we'll do. Yeah. Yeah. Okay, great. So, okay, so let's look at like a first basic method that will achieve this criterion. So we have our unlabeled data set xi. We're going to push this data set through the model F. We're going to get these AI predictions yi hat. And now, in addition, we're going to assume that we have access to some source of some notion of model uncertainty that we'll denote by UI. And throughout the talk, I'll talk about experiments on different data modalities, and we'll see different ways that we can collect these kinds of uncertainty scores. So for now, let's just take for granted that in addition to the prediction, we also have some access to uncertainty. One reasonable thing that you might do is just pick some uncertainty threshold U, and we collect expert labels if our uncertainty is higher than U, and we just go with the AI predictions if our uncertainty is lower than U. So this seems like a pretty reasonable thing to do. So then if you think about how to pick this threshold U. So now really the only thing that remains is how do we actually pick this threshold U? So you could think about the loss that's induced by picking a particular threshold U. Note that this is going to be a monotonic function because the higher my U is, the fewer expert labels I'm collecting. So in particular, if my U is really, really high, I'm going to incur a very high loss because I'm not going to be collecting a lot of expert labels, and my AI algorithm might not be that good. If I set the threshold U to be really low, I will meet the error criterion, but I might be too conservative. I might be over-collecting expert labels. I might be collecting more of them than I actually need. So intuitively, what I would want is I would hope to find this U star, which is the U where I exactly hit the error epsilon, because that's where I'm the least conservative. Now, of course, the issue here is that we don't know where this U star is because it depends on this loss function that's induced by picking U. We don't know that a priori. So what we'll do is we'll strategically collect points so that we construct a 1 minus alpha upper confidence bound on this function. And then we'll look at where the upper confidence bound hits the value epsilon. And we're going to denote that threshold by U hat. And if you formalize all of this, you'll get that these resulting labels are indeed pack labels. And on the next slide, we'll go through the proof. It's very short. So notice that this U hat is going to be to the left of U star because the upper confidence bound can only make things more conservative. Okay, so let's try to actually prove this a bit more formally. So by LU, again, we're denoting this loss that's induced by choosing a particular threshold U. If you look at these slides very carefully, you'll see that I'm being very strategic where I'm going to place strict inequalities and non-strict inequalities. So trust me that things are picked intentionally, even though sometimes they will look a little bit maybe they will look a little bit off. Okay, so we'll assume basically that we have this upper confidence bound L hat U. And we're going to assume that for all U, it's a valid 1 minus alpha upper confidence bound. So note that I'm not requiring this to be valid simultaneously for all U, but I'm only requiring it to be valid marginally at every U. And that's actually related to what we talked about yesterday in our working group. Okay, so I have my valid upper confidence bound, and I'm going to pick the smallest U where this upper confidence bound exceeds epsilon. Okay, so here's the proof. It's, I think, 4 lines. Step number 1, we define U star to be the smallest U where our real loss exceeds epsilon. Then, if I have this U star, my labels will be pack labels with probability 1, just by definition. So that's the first point where the loss crosses epsilon. So if I label everything from there on, my labels are going to be correct. or their error is going to be bounded by epsilon. Okay, so by the fact that this function is monotone, if I pick any more conservative u, I'm also going to have pack labels, right? Because if I pick any point to the left, that just means I'm collecting more expert labels. So really, the only thing we want to prove is that our u hat will be upper bounded by u star with probability 1 minus alpha. So let's proceed by contradiction. Suppose that u hat actually is larger than u star. Then by the definition of u hat, it must be that the upper confidence bound at u star is less than epsilon, because we said that u hat is the first u where I exceed epsilon, and u hat comes after u star. So that means that u star, the u hat was smaller than epsilon. But at the same time, by the definition of u star, we know that the true loss is greater than epsilon at u star. So that means that we're getting that the upper confidence bound is lower than the loss itself. And by the definition of a valid upper confidence bound, that can happen with probability at most alpha. So really, that's a 4-line proof of this basic argument. Okay, so this is the first basic version of the algorithm, and let's look at a few examples of how it performs in practice. So first, we'll look at a few text annotation examples, in particular from computational social science. I work with a group of computational social scientists at Stanford, and this is really inspired by the problems that they work on. So in this first example, we have the task of annotating political bias from a bunch of different media articles, and the annotation problem is to give the annotation of left-leaning, center, or right-leaning. And the question is, can we use large language models to basically speed up this annotation process? The second example that we'll be looking at is annotating article stance on global warming. So we have a bunch of media articles, and the goal is to annotate whether these articles agree with the claim that global warming is a serious concern, disagree with this claim, or are neutral. So again, our labels are agrees, neutral, or disagrees. In both of these examples, we'll use GPT-4o to collect the yi hats. For the uncertainty in this case, we're going to use verbalized confidence scores. So by that, I just mean you go to ChatGPT, it gives you an annotation, and you ask it, how confident are you in that annotation? That sounds totally silly, but we've actually tried different kinds of strategies for collecting confidences, and this seems to be the most calibrated one. By most calibrated, I don't really mean the classical notion of calibration. I just mean, for the purpose of this procedure, the only thing that matters is that the uncertainties are ordered in the correct way. The absolute value of the uncertainties doesn't really affect the procedure. And so what we see is that the uncertainties are ordered quite well, in the sense that as my uncertainty goes up, my accuracy goes down, which is what we would hope to see. Okay, and for the upper confidence bound, we use betting-based confidence bounds, so the work by Wadby, Smith, and Ramdas. Okay, and so here I'm showing you some results for the first example, for the media bias example. So going from left to right, I'm just varying the value of epsilon of my error threshold, so it's 5%, 10%, 15%. On the y-axis, I'm showing you the fraction of budget save, basically how many human labels we didn't have to collect because we are using GPT-4o. And on the x-axis, I'm plotting the realized error. So what is the realized error of our labeling? So by the provable guarantee, we know that this realized error has to be below this epsilon line. And here I'm showing you just 50 random realizations. So we can see in the first case, the average save is somewhere about 15% of labels. In the second case, it's somewhere closer to maybe 30. In the third case, I think it's over 30 on average. So we can see that we can save actually quite a non-trivial number of labels if we are allowed to use a large language model in the annotation process. And yeah, I didn't say the naive threshold baseline is, a heuristic where you just say, let me just label everything where I am less than 1 minus epsilon confident. So I'm just going to kind of heuristically collect some labels. I think in all of these examples, so here I think it exceeds the error very, very slightly. In all the other examples, it does end up being a valid baseline, but sometimes it's very conservative. So for example, here, this is where the naive threshold baseline is. So we can see that the budget save is basically on the lower end of what we achieve with pack labels, even though it does technically meet the error guarantee, although in a bunch of other examples that we've looked at, this is not always going to be valid, which is unsurprising. Yeah.
This question might be very naive because so it seems like here, if I'm understanding correctly, a lot of the points are very much left. They're very, very low error, so you don't, GP is very certain about it, and so you don't have to get expensive labels, which is great. I'm wondering, are those also the examples that somehow would be less informative for learning things downstream because they're somehow easy to predict, or am I thinking about this in the wrong way?
So I think so you're referring to the fact that some of these points are to the left of the vertical line. Is that right? Or to the left of
Yeah.
what?
So
Because I think that's just saying that the procedure is conservative in some of these cases. It's not like using up the error budget fully. The reason that's not happening here is because there are a lot of ties in the uncertainties, and I can say more about that. There is a way to fix this, but I'm not sure how that relates to the second part of your question. Can you repeat?
yes. So again, maybe I'm thinking about this the wrong way, but after all of this, you're hoping to have some labels which are good that you can use for a downstream task like maybe actually doing the regression for finding the function f or things like that.
Yeah.
So here your uncertainties are related to maybe slightly different, but related to how easy it is to sort of guess the function f. So
Yeah.
if we're going to use these labels later to learn the whole f.
Yeah, I see. Like if your goal is to improve the model that you in the first place used to label, yeah, I would say that this is probably not very promising because you're like collecting, you're mostly going to be, well, actually, no, sorry, I take it back. Yeah, you might actually be able to fine tune because you're collecting labels where your F was wrong. So I think, or not wrong, but where it thinks it might be wrong, right? Yeah, I think you could in principle. I don't necessarily, as the main use case, that's why I'm confused. As the main use case, I don't necessarily think about these settings where you're going to collect this label data and then you're going to like go and train a model. Like for example, these like computational social science problems that we're working on, the goal is just to answer a question like, oh, is the incidence of like right-leaning bias increasing over time, like after the Elon Musk acquisition or something, like questions like that. So the goal is not necessarily to train a model, but I think it's a sensible thing to do. Yeah, yeah. So I think this might be an okay strategy for fine tuning. Okay, yeah, and so the second example is stance on global warming. And so again, here we see actually larger saves. So with a 5% error guarantee, we see saves, around 30%. Here it goes like about 40%, 50%. So we can save quite a bit. Yeah.
This is not a question. It doesn't have my.
Just a reaction, a gut reaction.
Yeah, it's much higher than I would expect it to be in such a simple question. And 40% of error sounds like.
No, 40% is the save. That's like how many.
Yeah.
Oh no, this is like 0.5, 0.1, 0.15. Oh, you mean like what's the error of the AI only? Oh yeah, AI only is, yeah, if you just use GPT errors, it's high. Well, you have 3 classes. And the error is like 30%. I don't know, like.
Yeah, so that's
25.
Right? I'm a number, like it's not like.
I think it's hard to.
2.4 for AI for like labeling is this left or center, right? It sounds like very surprisingly high.
These articles are not easy. Like they're not. Yeah, I think if you had access to. Okay, I mean there are a lot of caveats, right? One is. you know, where are these like ground truth, like expert labels coming from? So in the case of annotating political annotations, there's a platform there's a company called All Sides that collects like expert, you know, annotations from experts on political bias, and you know, they have a whole art of their own on how they collect like expert human annotations. So the fact that, you know, even for them, it's like non-trivial to collect expert annotations, and you know, there's like a lot of experts that have to be involved to produce like one expert label. You know, that makes me feel like it makes sense for GPT-4o to not be able to reproduce that easily. Yeah. So anyway, but yeah, that's a good thing to point out. So if we just use AI labels, in the first example, we have about 40% error. In the second example, we have about 25%. Okay, so these are all text examples. Now I want to show you some image examples. So here we'll, of course, look at ImageNet, this large data set of like 1,000 random classes of objects, animals, and so on. So we'll have, you know, 1,000 possible classes. We're going to look both at ImageNet and ImageNet v2, and we're going to use a pre-trained ResNet that was trained on ImageNet for the annotation. So the question is, if I use a pre-trained ResNet that's trained on the training portion of ImageNet, how well can I do if I want to label the test portion of ImageNet? So note that this is within distribution. And then I'm also going to ask the same question for ImageNet v2, which is, you know, very similar to ImageNet, but there's a distribution shift. So you should think of this as being basically a distribution shifted version of the first problem. Okay, so again, F is a pre-trained ResNet. For the uncertainties, we're going to just look at softmax outputs. So we're going to look at how close the softmax output is to 1 of the predicted label. And again, we're going to use the same embedding-based upper confidence bounds. Okay, so here's what you get on ImageNet. This, you know, may or may not be surprising to you, but you know, there are 1,000 possible classes. If you set a 5% error budget, you're going to save about 60% of the labels. So basically, you know, the way you should think about it is if I now wanted to collect, let's say, an ImageNet v3, I might be able to do that while only collecting labels for about 40% of the points if I already have a good model that was trained on ImageNet. You know, if I make my error budget looser, like around 15%, I can save like over 80% of the labels. So the saves can be pretty high. But note that the pre-trained ResNet that I'm using is not actually that good, so it's not actually going to meet this error budget. If I just naively used the ResNet, I'm not actually going to hit the epsilon error, but the error is like 21%. Okay, and then, you know, perhaps unsurprisingly, if I go to ImageNet v2, it's going to look pretty similar, but the numbers are going to go down. So with a 5% error budget on ImageNet, we saved around 60%. On ImageNet v2, we're saving about 40%. So it makes sense because it's more out of distribution for the ResNet that we're using. Okay, but these are all classification problems and, you know, discrete labels. You might wonder, can I use pack labeling for, you know, more interesting tasks? So what if I go to protein folding and I'm wondering, can I somehow use AlphaFold to reduce the cost of protein folding experiments? Can I, you know, impute predicted protein structures? So, you know, first we have to define what is the loss, what are the uncertainties that we're using. So the loss is typically used in the literature is just mean squared deviation, or RMSD. And it's worth keeping in mind that the median RMSD between different experimental structures of the same protein, so even if I rerun you know, the same experiment for the same protein, I'm going to get an RMSD of around 0.6 angstrom. So there is some kind of lower bound that we can't go beyond. For the uncertainties, luckily, you know, AlphaFold has these local measures of confidence that are called predicted local distance difference tests, or PLDDT. So we're just going to use those for our uncertainties. And if we run pack labeling with RMSD of 0.6, then and the error level is and the probability is 5%, then we're going to collect about 73% of protein structures. So we're going to save about 27%. If we run it for epsilon equal to 1, then we're going to save about 36% of protein structures. Of course, the caveat here is that, AlphaFold was trained on everything that we know, right? All protein structures that we have, probably including the protein structures that we're using for this analysis. So, you should take all of this with a grain of salt, but, I think it's still an interesting proof of concept. Because note that, if we use AlphaFold alone, it actually doesn't hit these values of epsilon. So AlphaFold alone in this data set gives about 1.5 angstrom. So it does exceed these numbers. And in the literature, 1 is known as kind of like pretty good. Like 1 is a reasonable error guarantee. Okay, so this is the basic version of the algorithm. Now you might wonder, can I go to more interesting settings? Yeah.
Upper confidence, I guess you can be about where it comes from, but do you need your labels somewhere in that to take that?
Yes. So the way, sorry, I didn't clarify that fully. So the way that we'll construct the upper confidence bound is at the beginning we'll have a step where we collect a smaller amount of labels in some random way, or like strategically with some adaptive sampling, but still like randomly. And then once we have that, we can construct the upper confidence bound, even if it's completely uniform at random. That actually all the experiments that I'm showing are with uniformly at random collected. It's a hyperparameter, so it depends. It depends on like some other choices, like whether also downstream you want to use, whether you want to use like a non-asymptotic or an asymptotic confidence bound. Depends on like where you want to pay the price. But yeah, we don't have like a very clever way of picking this set size. For now, we're just treating it as a hyperparameter. Okay, so the way you can think about the method as I showed it is you can think of it as essentially taking all my unlabeled data points and essentially routing them to one of two sources of supervision, either the expert or the AI model. But there's really nothing stopping us from considering a bunch of different AI models and thinking about how do we actually route between all of these different models. So we developed this router that applies the pack labeling procedure, but carefully optimizes the final labeling cost. So I'll tell you a little bit about that. So by W theta, we'll denote the router. So by theta, we'll just, you should think of this as being, let's say, a neural network, and we're going to optimize this parameter theta. The first instinct you might have is, well, why don't we just learn a router that optimizes the accuracy of the labels? So it just, picks the AI model such that, that AI model is the one that's most likely to be correct for the given data point. Know that, that doesn't really tell me much about what is going to be the final labeling cost, because ultimately the labeling cost is determined by these uncertainties. So I need to consider some kind of criterion that involves the uncertainties to really understand how I should be optimizing the labeling cost. Okay, so basically by the definition of the procedure, this is the expected labeling cost once I use this router. Of course, we want to optimize this, but the issue is that, first of all, I have this indicator that's non-differentiable. And second, my threshold depends on the router itself. Because once I collect labels according to the router and I calibrate this uncertainty threshold, then the threshold is also going to have dependence on this theta. So the way that we circumvent this is, first of all, of course, indicator we'll just replace with a sigmoid. And for the issue B, we will use the implicit function theorem to approximately differentiate through the threshold and its dependence on theta. In particular, because we know what the procedure does, it does something very specific, which is it finds this value of u where my estimated loss hits the value epsilon. This would essentially be an approximation of my estimated loss induced by selecting the threshold epsilon. So through this, I can basically just back out the gradient of u with respect to theta. So this is kind of like the first version of the router that we came up with, but then you can do more clever things. In particular, what we realized is that with the first version of the procedure, something that didn't work as well is the uncertainties were still not necessarily calibrated enough. So, if we're throwing in this learning step, why don't we also try to learn a better representation of the uncertainties? Maybe we can aggregate the uncertainties over all of these different models and just learn a better uncertainty score for a given point. So here we're just going to add, another model that we're training, which is let's just learn a better post-processing of the uncertainties. And nothing really fundamentally changes when you introduce this model. There's a similar approximation into a differentiable objective. And also, everything that I've shown so far, it doesn't take into account that different AI models might actually have different associated costs, but we're still targeting this problem of let's just minimize the number of expert labels that we need to collect. But it's actually pretty easy to also incorporate costs. So we also have a cost-sensitive variant where for each model FJ, you can have an associated cost CJ. And again, similar tricks apply. And so I want to show you one plot that I think is really cool. So we ran some experiments where we tried incorporating this router and routing between GPT and Claude. And so here, this is basically the loss function that I'm getting for pack labeling for different choices of U. So on the x-axis is U. I just basically mapped U to their index. Because again, the only thing that matters from the uncertainties is their ordering. So without loss of generality, we can just map them to integers. And we map them in such a way so that we can kind of directly compare these three procedures. The point at the very end for the largest U, that's the final accuracy of that model. So the accuracy on the whole data set that I need to label. So we can see that Claude alone has sorry, not the accuracy, but the error. So Claude alone has 40-something% error. GPT has something a little bit lower, 30-something%. We can see that the router, it does decrease the error, but it doesn't decrease the error all that much. So even though we're routing between these two models, the final error on the whole data set is not that much better. But what is much better is how the uncertainties are ordered. In particular, how many, what is the error on the data points that have, an uncertainty before this 0.05 line. So we can see that there's exactly a kink at this 0.05 line because of how we've set up the objective. And so we can see that, if I label, because I'm going to label everything starting from the point where I had hit the 0.05 line, so we can see that with the router, I'm only going to have to label these points, whereas with these other two models, I'm going to have to label all of this. So the fact that, the magic is really in the fact that it makes the curve really, really flat at the beginning before the 0.05 line. Okay, so this is on the same media bias example that we saw before, and this is what the results look like. So again, as the other two baselines, we're going to be valid. We're going to be with high probability below this vertical line, and you can see that in terms of how many labels we're able to save, that we actually exceed these two baselines by quite a bit. The first version of the plot is just saving the number of labels. But then if we, in addition, incorporate costs, so these were the current relative costs of GPT and Claude. I don't know if that's changed. We can see actually, so this is what I found kind of interesting. So we can see that there's quite a bit of overlap between GPT and Claude, which makes me think that these things are actually priced well. I don't know. This was very surprising to me. But if you apply the router, you're able to actually save quite a bit more. Here, I just want to show you some final examples with asymptotic confidence intervals. So as I mentioned, for this upper confidence bound, you could consider using both asymptotic and non-asymptotic confidence bounds. In everything that I've shown so far, we used non-asymptotic confidence bounds, just to make the guarantee fully rigorous, because the argument on the validity of pack labeling, it doesn't really depend on, there's nothing asymptotic about it. It's just an exact non-asymptotic argument. But here, we looked at what will happen if we use an asymptotic procedure, because if we use an asymptotic procedure, that gives us a little bit more wiggle room, and we can actually squeeze out a larger save. And that's exactly what you see here. So the top row is non-asymptotic results. So you already saw these plots a few slides ago. The bottom row is asymptotic results, and we can see, maybe here, when epsilon is 0.15. With the non-asymptotic procedure, we save about like 30%. And here we can save, quite a bit over 40% or even more. But of course, the flip side is that, we do make errors occasionally. So, the error does fluctuate pretty tightly around, epsilon, but alpha, but, it might exceed alpha by some small amount. Okay, so zooming out, I think that there's just a very interesting direction around understanding how to reliably trade off between different data sources of varying qualities and costs. I think, with this explosion of AI, and we've talked about synthetic data also yesterday, Edgar talked about synthetic data. I think there are a lot of interesting questions around, how to actually incorporate these synthetic, cheap sources of data with expert source. And the reality is that there are really many of these synthetic sources. All of them have different costs, different qualities that are unknown to us a priori. And I think there's a lot of interesting statistical questions and kind of understanding how to reliably combine them. There's also a huge amount of interest from more applied and scientific disciplines. So, I've also kind of thought about these types of problems in a scientific context, but here you can see, a bunch of applications of how people are using this in computational social science, sociology, and, NLP, and much more. So I think that there's really a lot of room for very interesting theory in this space. And with that, yeah, thank you for listening, and I'm happy to take my questions.